Yo, what's going on guys, Tanmay here for Simple Snippets and welcome back to another video tutorial on data structures and algorithms, and we're gonna continue with the tree data structure. And as the title of the video suggests, today we're gonna take a detailed look at binary tree data structure. So in the previous tutorial we took an introduction to tree data structure and how it is different from other conventional linear data structures. We also briefly talked about binary tree because we're going to see a lot of binary tree data structure variants as we move ahead in this tutorial course. So it's about time that we take a detailed look at binary tree data structure and understand in depth about its different terms, about its different properties, about how it is implemented and different variants. So with that being said, let's get started. If you're new to my channel, my name is Tanmay Sakpal and I do a lot of computer science and information technology video tutorials like computer programming, development, technology talks and a lot more on this channel. So if that's something you're interested into, then definitely subscribe and turn on the notifications to get the latest updates and never miss out on such important topics. So quick definition to binary tree, which we've already seen, but just to reiterate, a binary tree, as the name suggests, is a tree data structure in which each node has at most two children, which are referred to as left child and right child. Okay, so it's a special type of tree wherein every node can only have maximum two children and they are referred as left and right child. So in general, a generic tree can have multiple children. So every node, it can have 1, 2, 3 and n number of children. But binary tree is a special kind of tree where you can have only two children per node. Okay, so that's the unique definition of a binary tree. And now let's try to figure out some more important terms and properties of a binary tree. So on the right hand side, you can see we have a binary tree. We have the root node, which is numbered as number 1. For the root node, number 2 and number 3 are the nodes which are left child named as LC. I'll give short term as LC, and RC for the right child. So you can see we have only two nodes. For this node number 2, we have 4 and 5 as LC and RC. For node 3, we have 6 and 7 as LC and RC. And lastly, for node 6, we only have a left child. We do not have a right child. Okay, so that part programmatically, if you see, it is gonna be null. So of course, a binary tree can have one child, but it cannot have more than two. Okay, so the condition is you cannot have more than two. You can have none or you can have one child. So you can see the leaf nodes do not have any children. So that is also valid. It is just that it cannot have more than two children. Alright, so that's the definition. Okay, let's move forward and let's see some important binary tree terms and properties. So first point, a binary tree is called a strict proper binary tree when each node has 2 or 0 children. So a variation in binary tree is a binary tree is called a strict or a proper binary tree when each node has 2 or 0 children. So currently in our example, you can see that this node 6 has one child. So hence it is not a strict or proper binary tree. So what can be a strict or proper binary tree? Let's see some variants. So over here in this first example, I have one single node. Let's call it root because that's where we start with the tree data structure. I'll name it 1. And you can see it does not have a left child or a right child. So both of them are missing. So this can also be considered as a tree data structure, right? A tree can have one single node as well, which is also the root node. So it has 0 children. So this condition is met, which means that it is also a strict or proper binary tree. Let's take a look at this. Example 2. Over here, if this is the root, if we start from over here, and this is the second node and this is the third node, this can be considered as a binary tree. Of course, it is falling in the definition. A binary tree states that each node can have at most 2 children. So it can obviously have one children. So this root node has a left child. Then node 2 also has a left child. They do not have a right child. This also doesn't have a right child. And this is the leaf node, so it doesn't have a left or right children. But this is also a binary tree because it falls under the definition. But is it a strict or a proper binary tree? No, because it has to have either two children, that is every node should have either two children or no children. They cannot have one child. So this is again not a strict binary tree. Let's take a look at this. Just by looking at it, you can say that this is also not a strict binary tree because let me number it. node 2 and 3 have only single children. So if there were a right child and a left child like this, so then it would be a strict or a proper binary tree. Okay? So if you're wondering why we are learning these terms, it is because these terms will be used further when we move forward with the implementation and when we see more variations in binary tree. And of course, some of the variations, that is some of these variants, also have their unique properties. So it's better to understand and keep these terms in mind. Let's move to point number 2. A binary tree is called a complete binary tree if all levels except the last are completely filled and all nodes are as left as possible. Okay, so we just saw what is a strict or a proper binary tree. Let's understand what is a complete binary tree. So complete binary tree states that it is a binary tree if all levels, so when I say level, you start from level 0 as the root. So let's take an example. So over here if you see, this is the root. Okay, so the root usually is considered as level 0. Okay, once we traverse from root to the immediate child, it is considered as level 1, and then we have level 2. Okay, so what this second point is saying is a binary tree is called complete binary tree if all levels except the last are completely filled and all nodes are as left as possible. So over here looking at this level 0, that is root node 1, it has 2 children, which is the maximum a binary tree has per node. So this is full, which means that you cannot have more children. Then coming at level 1, observing node 2 and 3, both 2 and 3 have 2 children. So they cannot have more than 2, which means they are full. That is, they are completely filled. And below that, obviously, there is no nodes because that is the last level, level 2. So 4, 5, 6 and 7 nodes are leaf nodes. So is it a complete binary tree? Yes, because all levels except the last are completely filled. Except the last, which means the last level which is at leaf position, because obviously since it is a leaf node, it will not have any children. But all other nodes are completely filled, which means they each have 2 children. Now there is one more condition, that is if they are not completely filled, they need to be as left as possible. So what does this mean? So taking this example, again starting from root, let's say this is the root and this is level 0, 2 and 3 are at level 1, 4, 5, 6, 7 are at level 2 and 8 is at level 3. Okay, makes sense? Now is it a complete binary tree? If you observe level 0, level 1 are completely filled, which means each node at level 0 and level 1 have 2 children. So coming at the last level, that is level 3, we have 1 node, but this is not to the extreme left. When you talk about level 3, that is the last level, it has to be at the extreme left, which means that this 8 has to come over here and it has to be left child LC for this node 4. Only then it can be considered as a complete binary tree. But since there is some room left to the left side of the last level, it is not a complete binary tree. So if you want to make it complete binary tree, you have to remove it from this position and take it over here as the left child for node 4. It cannot be as a right child. Okay, remember, it cannot come to the right when you have some place at the left. So in case you don't have a place at the left, let's say 8 is over here and you want to add one more node, which is node 9. So you cannot add node 9 as the left child over here as long as you have some place for the right child at this place. So 9 should come over here because there is some place towards the left. Okay, so when you fill in nodes, they have to start from left to right. So the leftmost node at level 2 will get filled first, starting from left to right, that is left child first, then right child, and then you move to the next node. Then you fill these two and then you move ahead. Okay, and that's how you get a complete binary tree. So again, repeating the definition, a binary tree is called complete binary tree if all levels except the last are completely filled. So the last one, if it is incompletely filled, that is okay, but it has to be as left as possible, which means that the node at the last level has to be at the leftmost side. Okay, so that defines a complete binary tree. And the last one is a binary tree is called a perfect binary tree if all levels are completely filled with 2 children. Of course, when I say all levels, it means that the last level excluding, because the last level would be leaf nodes and leaf nodes do not have children. So taking the same example, we have 3 levels, right? So this is level 3, but level 3 has only one node, so this is not a perfect binary tree. It would be a perfect binary tree if node 4 has 2 nodes, let's say 9 and 10. Node 5 has 2 nodes, 11 and 12. Node 6 has 2 nodes, 8 and 13. Node 7 has 2 nodes, 14 and 15. Now this binary tree can be considered as perfect binary tree where every node has 2 children each. Okay? Of course, leaving the last level, because at last level we have the leaf nodes. So I hope these 3 different types of binary tree depending upon the number of nodes and the arrangement is very clear. Let's move forward. Now here's another property of binary tree, which is point number 4, which says maximum number of nodes at any level x is equal to 2 raised to x. So again, starting off with this binary tree, which is also a perfect binary tree, because if you observe, all the levels have completely filled with the nodes. So this is root, this as I mentioned is at level 0, this is at level 1, and this is at level 3. Okay, so maximum number of nodes at level x is equal to 2 raised to x. So let's test this at level 0. So at level 0, that is when x equals to 0, what is 2 raised to 0? It is equal to 1. So you can see we have only one node at level 0, which is obviously the root node. So when x equals to 1, we have to say 2 raised to 1, which is equal to 2. So at level 1, you can see we have maximum of 2 nodes. Obviously, below the root, we can only have 2 nodes as maximum number, because that's the definition of a binary tree. When we say x equals to 2, it is 2 raised to 2, which is 4. So at level 3, you can see it is completely filled, which means you cannot add more than these number of nodes, and these number is 4. So this is a basic formula. Moving on to another formula or another property. So for a binary tree, maximum number of nodes with height h is given by this formula 2 raised to 0, which is at level 0, plus 2 raised to 1, which is at level 1, plus then it keeps on going, and 2 raised to h is the height. I hope you know what is the height of a tree. We've seen it in the previous tutorial, that is the definition. So the height of the tree is defined as the height of the root node, and the height of the root node is the number of edges from the root node till the leaf node, and you have to take the maximum number of edges which comes between the root node till the leaf node. So the root node is node 1, and let's say this is the leaf node because we have only 3 levels. So the height is gonna be this one edge, because we go from 1 to 2, so this is 1, and then we go from 2 to 4, so this is 2. So height is gonna be 2. Okay, so the height of this tree is gonna be 2 and not 3. We have 3 levels, but the height is 2. Okay, don't get confused. And the formula is as follows: 2 raised to 0 plus 2 raised to 1 plus 2 raised to h, which when condensed we get 2 raised to h plus 1, and then we have minus 1. So let's try to apply this formula. We know the height of the tree over here is 2. So the maximum number of nodes in this tree that can happen is 2 raised to, what is the height? 2 plus 1 minus 1. So it is equal to 2 raised to 3 minus 1, which is equal to 8 minus 1, which is equal to 7. Now if you calculate, this is also a perfect binary tree, which means it is completely filled with all the nodes. You can see we have 7 nodes, which is exactly what we got over here. So just in case, just to clarify, if we had one more level or one more value added to the height, how many number of nodes do we have? Let's apply this formula again. The height now would become 3 because we have 4 levels, and we have 2 raised to 3 plus 1 minus 1, which is equal to 2 raised to 4 minus 1, which is going to be 16 minus 1, which is going to be 15. So let's calculate the number of nodes, maximum number of nodes in this binary tree. We already had 7, then we have 8, 9, 10, 11, 12, 13, 14 and 15. Okay, so you can see this formula holds true. Please make a note of this formula. It can be asked and you might be given the height, or you might be given the number of levels, or you might be just given a tree diagram and you will be asked to calculate the maximum number of nodes that that particular tree can have. So this formula can easily get you that answer. Okay, alright, let's move forward. Okay, so the last point I want to discuss briefly is the concept of dense versus sparse tree and the concept of balanced binary tree. So a binary tree is called balanced binary tree if the difference between the height of left and right subtree for every node is not more than k, and it is usually considered as 1. So what is this balanced binary tree? So before understanding what is balanced binary tree, let's try to understand what is dense versus a sparse tree. So a dense tree usually is where the distribution of nodes is fairly even on the left and the right hand side. So over here, if you see, the arrangement is in such a way that at level 0 you have 2 children, that is 2 and 3, and at level 1 the first node has 2 children. So when you add more nodes, it will be added over here as 6 and 7. So a dense binary tree usually has a balance of both left and right child always, and it does not prioritize assigning nodes in one particular direction in left or right. Okay, so compared to this diagram over here, you can see if this is the root, you can see that this root node 1 has a left child. So this is level 0, then this is level 1. Again at level 1, node 2 has another left child, so this is level 2. Again node 3 has another left child, node 4, which is at level 3, and node 4 again has one more left child, node 5, which is at level 4. Now this kind of scenario is called a sparse tree scenario. We'll discuss more about these two different types in detail, and also what is balanced tree in detail. I just wanted to give you an introduction. But now if you want to traverse to node 6 in the dense tree, how many hops do you require? You will obviously start from the root. The root is node 1. So you can see you'll go from 1 to 3 and you'll go from 3 to 6. So you require 2 hops. Similarly, if you want to access node 5, you'll go from 1 to 2 and you'll go from 2 to 5. Again 2 hops. In the sparse tree, of course this is also a valid binary tree, but it is sparse in the sense that all the nodes are assigned in one direction, and it pretty much looks like a linked list, to be honest, right? A linked list also is exactly like this. So in order to get to 5, that is node 5, how many hops do you require? You go from 1 to 2, so this is 1. Then you go from 2 to 3, it is second hop. Then you go from 3 to 4, it is third. Then you go from 4 to 5, it is fourth. So how many hops do you require? You required 4 hops. So in a dense tree, node 5 was accessed in 2 hops. In a sparse tree, node 5 was accessed in 4 hops. So you can see that the efficiency is more in a dense tree, which means that in less amount of time, we are accessing the particular nodes. So if it took 1 second to make 1 hop, it would have taken 2 seconds in the dense tree to go from 1 to 5, and it would have taken 4 seconds, which is double the time, to access node 5 in the sparse tree. Now this was just an example. In real world scenarios, the binary trees are having multiple levels, and that level value is large, so you have hundreds and thousands of levels. And if in that case, if it is a sparse tree, the time required becomes exponentially high, and we'll discuss the difference in the time complexity also later on. But you get the idea, right? If I just add 2 more nodes over here, so 5 goes to 6 and 6 goes to 7, so 2 more levels are added. If I wanted to access node 7 in the dense tree, I'm again gonna require only 2 hops, from 1 to 3 and 3 to 7. Again 2 hops, 2 seconds if it takes 1 second for 1 hop. But to access node 7 in a sparse tree, I'm gonna require 4 plus 5 plus 6, that is 6 hops, that is 6 seconds. So 2 seconds on the dense side, but 6 seconds on the sparse side. So you can see the time is substantially increasing as the number of levels increase, and that is the reason why we want to have minimum number of levels. So we try to convert a sparse tree into this dense kind of tree by rearranging the nodes in this format and try to balance it. So this is where the concept of balanced binary tree comes into picture, and let's see what a balanced binary tree would look like. So again, going through the definition, a binary tree is called balanced binary tree if difference between the height of the left and right subtree for every node is not more than k, which is usually 1. Okay, so let's take example 1. So this is the root node. What we have to do, we have to calculate the height of left and right subtree. So for node 1, this is the left subtree and this is the right subtree. What is the definition of height? The height of a node is defined as the longest path from that node to the leaf. So the height of this subtree, where for the subtree this is the root node, and then the height of the tree is gonna be the longest part from the top till the bottom. So you can go from 2 to 4 or 2 to 5. The height is gonna be 1 because we are requiring 1 hop. And when I say path, it means this edge. We have to calculate the number of edges from the top till the bottom, which is the longest path. So for left subtree, the height is 1. So I'm gonna write 1 over here. Let me use another color. Let me write 1 over here. For the right subtree, of course, this is also a tree and this is the root node. What is the height of this subtree? It is gonna be 0 because it does not have any child. So we don't have any edge to hop on. So I'll write 0 over here. So difference between the height of left and right subtree is 1 minus 0, which is equal to 1. Okay. Now you also have to calculate the height for this and this as the left subtree and right subtree for this node. So for this node, this is the left subtree. Even though it does not have any further nodes, it is also considered as a subtree, right? One single node in this format is also considered as a subtree. So over here, the height of this node is going to be 0. The height of this node is going to be 0. Obviously, the difference is going to be 0 also. So this is considered as a balanced binary tree because the difference is not more than 1 for any subtree. Because you have to calculate it for every node. We did it for every node and it is not more than k, which we are considering as 1. Okay. So I hope you are getting this. Now let's calculate the same height of left and right subtree for this second example. So 1 being the root node, the two different subtrees, that is the left subtree is this one and this is the entire right subtree, right? So for this as the left subtree, what is the height? So this has to be the root for this subtree and the height of this tree is going to be the number of edges from the root till the leaf, which is the longest path. We only have one edge between 2 and 4. We only have one edge between 2 and 5. So the longest path is 1. So height I'll write as 1. On the right subtree, what is the height? So this is the root, which is 3 for this subtree. We have one hop over here. We can go from 6 to 8, but we can go from 6 to 7 and 7 to 9. So 2 hops over here, 2 and 3. So the height of right subtree is, you can say, 1, 2 and 3. So I'll write 3 over here. And the difference between the two is 1 minus 3. You have to take an absolute difference. So you have mod and height of left subtree minus height of right subtree. So 1 minus 3 is going to give you minus 2 and remove the minus. So we have a 2. So now this is not a balanced binary tree because the difference between height of left subtree and right subtree is more than the value k, and k we are assuming as 1. So this is not a balanced binary tree, and in future videos we'll understand how to convert this unbalanced binary tree into a balanced binary tree. And the reason why we want a balanced binary tree is because the traversal of a balanced binary tree is more cost efficient when it comes to accessing the different nodes, and if it is unbalanced, reaching the leaf nodes from the root takes more time. So if this was a balanced tree, 7 could have come over here, 8 could have gone over here, and 9 could have gone over here, and you can see we get one less level. So accessing 9 will take 1 unit less time, and you'll understand in detail as we move forward. Right now I just wanted to give you a brief about balanced binary tree and how to understand which tree is a balanced binary tree and not. So I hope you got the calculation and the definition of a balanced binary tree. So let's move forward to the last topic of this video, which is how you can implement a binary tree data structure. Now in the previous tutorial we saw one type of implementation of binary tree, and that is as dynamic nodes in the memory. When I say that, you just create a node. You can see I've created a node n1 in the memory at some address #10, Then you create node n2 at some other address #23, and for node n1 as the left pointer you assign n2. So n2's address of 23 is stored as the left child address, and for the right child you assign n3, which is again created at some other memory location #27. So #27 is stored over here as the right child, and pretty much that goes ahead also. You can see we've created n4 at #73, and that is stored as left child in n2's left pointer, and for the right you have #66, which is n5's address, and so on and so forth. So this is how you pretty much create linked list also. So similarly you can create binary tree as dynamic nodes in the memory and link them using the left and right pointer methodology. But there is one more way of creating binary tree, which is by creating conventional arrays. Yes, you can create binary trees in arrays. So array is another data structure, but you can use it to work like a binary tree. So how does that work? So let's say we have this binary tree. Every binary tree has different nodes. So this node has value of 4, which is the root node. So this is the root node. Then we have its child node, that is left child and right child, and both have value of 9 and 3. So this binary tree is storing integer values. Let's just assume it is storing integer values 4, 9, 3. Then we have 1, 5, 7 and 2. Okay. So in the pink over here, what I've done is I've just named these nodes starting from 0 and from left to right, level by level. So for level 0 I've named 0 for the root node. Then from the next level I'm saying 1 to 2 from left to right. Again I've said 3, 4, 5, 6. So I've named them chronologically from top to bottom, from left to right. So 0, 1, 2, 3, 4, 5, 6. And at the bottom you can see we have a basic array, ARR. And what we've done is, in the array we've stored these tree values at every node in such a way that it follows a particular formula, and that formula is given over here, that is for node at index I. So at every index I, so this is the array index 0, 1, 2, 3, 4, 5, 6. Obviously array index starts from 0, and for every index the way we store the value for this binary tree is given by this formula. For left child you have to say 2i plus 1. So the first root value you store as it is. So root value is 4, you can see. So this is the index position 0, and 0 index position we've stored 4. After that, of course, the root node has a left child LC and right child RC. LC is 9. So 9, where do we store in this array? It is given by this formula 2i plus 1. So for the node at index I, so which node is there at index I? It is the root node, and the index value is 0. So for the node at index I equals to 0, the formula will be 2i plus 1 for left child. So I is 0. So when you substitute 0, this becomes 0, and the left child you get the value of 1. So what is left child equal to 1? It is the index position 1 where the left child is stored. So 9 is stored at index position 1. Similarly for right child, let me write it over here, RC, we have the formula 2i plus 2. So again the root node is at index 0, so we substitute 0, so we get 2. So at index position 2, we store the right child for the root node. So the root node for left child is 9, for the right child is 3. Now again, for 9, you have left child and right child. So how do you calculate where you store these children in the array? With the same formula. And the formula is shown over here on the screen. You can try and apply it yourself, and you'll get the different index positions where the values have to be stored for the left and right child for every node. And this is how you can store data in an array for a binary tree. So a binary tree data can be stored as conventional arrays also, but typically it is done for perfect binary trees because all the nodes have to be filled. Otherwise we will have some gaps in the array where the values will not be stored. Okay, so this was a detailed video on binary tree data structure and the different variations, the different terms, the different properties. And we also saw what is dense tree, what is sparse tree, what is a balanced tree. Lastly, we also saw the implementation side of a binary tree data structure and the options in which you can implement a binary tree data structure. So I hope you've understood the entire concept of binary tree data structure. As we move ahead, we'll see more different variations and we'll also go through the implementation of binary tree data structure. If you like this video, please give it a thumbs up. Let me know in the comments how this video was. Do share it with your friends and I'll see you guys in the next one. Peace.